Hi everybody, this is our statics lecture number 12 covering section 3.2. So if you look at our Moodle page, what you'll see is this. I've printed off the notes, which are going to be in the background of my lecture today, so you can print them off if you'd like or follow along with them. And then the lecture for today will be here with the link rather than the assignment page. So getting started. There are two big skills that we learn in section 3.2, both of which have to do with vector multiplication. The first is called a scalar product, or is sometimes called a dot product. So there are sort of two definitions of the magnitude of a scalar product. And one, the vector p dotted with the vector q, the value will equal the length of q times the length of p, or the magnitude of p times the magnitude of q, times the cosine of the angle in between them. The same value will be found if you take the x components of those two vectors, multiply them, the y components of the two vectors, multiply them, and the multiplied value of the z components multiplied together, add all three. So if we combine these two ideas, we can come up with an expression that can actually help us find the cosine between two vectors. And this is actually pretty useful. So a couple of things to note is that the scalar product itself is, of course, not a vector. Dot product is a scalar. So even though you start with two vectors, the product that you come up with when you multiply is a scalar. That means it does not have the directional properties, it does not have components, but is just a number and possibly a unit. Possibly. Anyway, so you can use the scalar product to find the angle theta between two vectors. Now, one thing to know about scalar products is they are distributive. If you remember, we don't really have a distributive property that applies to the cross product being the vector product, which is, of course, a vector. But the scalar product is distributive in that you could add two vectors together and then dot them with a third, or you could distribute that first vector through. But even in this case, because it's a scalar product, the answer is, once again, a scalar. No components, no ijk, none of that. Now, one application of a scalar product, and one of the things that we'll be doing in this class, is the projection of any vector in any direction. So what that means is how much of the vector occurs in some direction, some random direction. Now, sometimes it could be random and sometimes it could be meaningful. One of the applications for this, for example, is the projection of a moment about an axis. And one of the applications for this is, if you think about, like, if you had a cedar chest or a rectangular trunk of any sort with a hinge, regardless of how you push on that lid, the only piece that's really going to open it up is the piece of the moment, the component of the moment, or the projection of the moment that's going to occur on that hinged axis. There are other physical applications, but at this point, that seems to be the most important. So you can find, or at least the most accessible, so you can find that scalar projection of any vector by taking the vector itself and doing the scalar or dot product with lambda in the direction of the axis. So in other words, with the example that I was just talking about, let's talk about a moment, for example, and we know that a moment is r cross f. But if we had that axis, like that hinged axis, if we found lambda on that hinged axis and then dotted it with the moment, where r, I've outlined this, r is any vector from any point on the axis, OL in this case, to any point on the line of action of the force F. If we take that and cross it with the force itself, this would be, of course, a vector, and then if we dot it with lambda along that axis OL, we would have a scalar product. Now, mathematically, to do that, we can actually form a determinant. If you recall, when we were doing cross products, this top row would be I, J, and K, which are the unit vectors, of course, in the x direction, the y direction, and the z direction. Here, lambda x, lambda y, and lambda z are the components of the unit vector along that axis OL. So you would find the vector OL, then you would find the magnitude of the vector OL, then you would divide the vector by the magnitude, and you could think of it as being the directional cosines, or the projection, or excuse me, or the components of the unit vector in the ijk directions. Then, having said that, going back to this equation, lambda, components on the top row, r, components on the second row, f, components on the third row, then we evaluate that determinant to find the vector projected on the axis. Right, so as an example, I did problem 3-39, so that you'll have this in your notes. And 339 is in your textbook. But basically, we have a tension of 280 pounds in a particular direction, the direction being cable AC, and then we have a boom that this is attached to. So at this point, I would recommend that you take out your textbook and look at problem 3.39. But we have the cable, which I wrote based on the dimensions in vector form, and the boom, which I wrote in dimensions in vector form, and I ask what is the angle between the boom and the cable. Well, I know from the first piece of work up here with my dot product that if I could define those two vectors, that I could use this idea and find the cosine of the angle between them by taking one definition of the dot product, dividing it by the other definition of the dot product. And then that would be the inverse cosine of the angle. So that's actually what I did. So here on 339, I found this vector and I found that vector. To find theta between them, I found AC dot AB by just taking the x components, -6 and -6, multiplying them, the y components, 6.5, -4.5, and the z components, 0 and 3, which of course 3 times 0, anything times 0 goes to 0. Reducing that and finding the number, which is 6.8. Now, if I go back to that definition again, the next thing I have to do, so I found this right here. The next thing is I need to find the length of P and the length of Q in order to divide what I've just determined in order to find the cosine of theta. So I go back to my work. I then find the length of AC by the Pythagorean theorem, the length of AB by the Pythagorean theorem, and then if I multiply them together, that would be P times Q, or in this case AC times AB. I take the 6.8, which is what I got in the first part, divide it by the product of 9.3 and 7.5 right here, and that is theta. So I take the inverse cosine of that number, and I get my value of theta of 84.4 degrees. So using the scalar product, I'm able to determine that the angle between those two vectors in three-dimensional space is 84.4 degrees. So that's in the plane in which they both exist. So that's pretty cool. It's a very powerful technique for finding that geometry. All right. Now, the other thing they ask is, let's go back here to problem 3.9. They ask you to find the projection of that vector onto a different axis. So in other words, they want to find the projection of a force of AC, which is the cable. So they want you to find the piece of the force that is projected onto AB, or how much of the force is being directed along the boom. Well, that's defined as the dot product between the tension and the unit vector along the boom. So this is the same geometry, it's the same picture from your textbook of 3.39, and so we've already found TAC. We know that it's 280. That would be the magnitude. Then we need to find lambda along AC because we know that the vector tension, TAC, is equal to the magnitude of the tension times lambda along the cable. So we find lambda AC the same way that we have in the past. We take the vector, divide it by the length, come up with those directional cosines or components of lambda. Then we multiply 280 through that expression to write the tension vector for AC. All right, the next thing we need is lambda along AB, or in other words, the unit vector along a boom. So we take the vector AB, which is the boom geometry, divide it by the length of the boom, and come up with the directional cosines, or the components of the unit vector along AB. All right, so after we do that, we take those two values. This is the force AB. This should be labeled lambda along the boom. We dot together. In other words, we multiply the x components together, multiply the y components together. Over here, the j component is 0, so that goes to 0, but we have two products, add them together, and we get that the force of the cable AB directed along the boom AC has a magnitude of 27 pounds. All right, so that is enough to get you started on your homework. I assigned 3 more problems. If you look at our Moodle page, you'll see that, there we go, you'll see that here in the submit homework number 3, I have submitted or I have added the second problem set. So the problem set 3.1, 3.3, and 3.22 is from section 3.1. The second problem set 33, 40, and 57 are from section 3.2. So please let me know if you have any questions. Keep working on this. And on Monday, we will do the lecture for section 3.3. And this particular chapter only has 4 sections. So after we finish 4, so this one will be on Monday, this will be on Wednesday, Friday we'll have a problem solving session and submit homework number 3. We will not have any quiz, just the homework for 3, and then the following week we'll get started on chapter 4. Now, the skills that we were doing in chapter 3 are going to pull directly over into chapter 4. So if you do really well with chapter 3, you will find chapter 4 to flow naturally from that and not be too much more material to learn. So that's it, everybody. Have a great weekend. I will look forward to seeing you Monday.